talking about an alternative measure of computation.
Okay. So this is in some sense, it's a completely different topic because it is not so much focused on learning, and it's not so much focused on, definitely not about statistics. I think so. Well, how do we know it is on?
We're blowing it. Yes. I will edit that out of the video.
Okay. So it's not about statistics at all, but what it does have in common with what I was talking about in the previous two talks is that it has to do with this distinction that I'm kind of really trying to make people aware of between worst case analysis and real data. But a different twist on the same kind of theme. So I'm going to talk about alternative measures of computational complexity with applications for machine learning, and I will focus on clustering. So what do I want to talk about? There are many problems that are theoretically hard, but they're practically feasible. And I think the most striking phenomena is the satisfiability problem. I mean, when I was a student, when you wanted to show that some problem is hard, you show that you can reduce SAT to this problem. Therefore, it's a proof that your problem is hard. 20 years later, when someone wants to solve a problem, they take their problem, they translate it into SAT, and feed it to a SAT solver. So in order to find an easy solution, you translate it into SAT and feed it to a SAT solver, and SAT solvers are now very efficient, and they do miracles, and they solve instances of hundreds of variables. Still, SAT is NP-hard. So how do we settle this inconsistency? And we don't have a good answer. And that was my motivating problem when I started working on it, and I had a PhD student that started working with me on trying to show how to explain the success of SAT solver in spite of the difficulty of SAT. And after a while, I decided that if I ever want this PhD student to graduate, then they should switch topic. But it still serves as a motivation. So another example is linear programming, and that's a very famous success of Spielman and Tang, that linear programming is supposed, theoretically, it's NP-hard. We have algorithms that, like the simplest algorithm that work in practice, and then they could show with some different analysis that under this smooth analysis, you can explain why it is working in practice. Another problem is neural network training. We know that neural network training is supposed to be NP-hard, but people are doing it routinely. And the problem that I'll focus on is k-means clustering. Again, it's a problem that we know that it's NP-hard. It is being solved routinely. We want to understand how come it is being solved in practice when it's hard in theory. So here is an outline of what I'm going to talk about. So I'll start by listing some machine learning tasks that we can prove that are NP-hard, just to have a collection of concrete problems to think about. Then I'll talk about how to relax the notion of success of an algorithm, and the relaxation will be in the spirit of what I was talking about in the previous two talks. I'll talk about requirements from the notion of natural inputs versus unnatural inputs, and I will allow my algorithm to run more time as the input becomes less and less natural. So the conclusion will be that algorithms run efficiently on natural algorithms. The reason they are NP-hard is because they get stuck on the unnatural. And then I'll show an efficient algorithm for all those problems under my notion of natural data. And at last, I will make this. We started this kind of project quite a while ago. The first paper on this was in 2000 with Harmon in 2000 NIPS, but it didn't catch any attention of the community. In 2010, Lineal and Binu and Lineal had a very influential paper on the same topic, and since then there are lots of people working and lots of new notions this direction are coming up, so I'll talk about such notions, alternative notions as well. Okay, so the basic rationale is that for many computational tasks, naturally arising inputs are considerably easier than worst-case instances. So this kind of rationale I've already discussed from a statistical point of view when I talked about, like yesterday, about the usefulness of unlabeled data. In worst case, it's not useful. On practically arising inputs, they are not as bad as worst case. And so SAT is one example. The question is, can we define clearly what are natural inputs in such a way that we will be able to show that on natural inputs we have efficient algorithms? So we want some properties that distinguish naturally occurring inputs from the worst case scenarios. And then we want that such inputs will be easy to solve. And we want to formally be able to distinguish this for specific tasks. A more ambitious challenge is whether we can find some such a generic definition. So here I'll talk about a definition that captures this notion of naturalness and efficiency for some specific task. But as I told you, I don't know the answer for SAT. So there is a question of whether you have a notion that will work across different problems, or we'll have to come up with a notion of naturalness, which is specific, different specific notion for every problem we want to tackle. Okay, so if we look at hardness proofs, we look at, I don't know how much you remember hardness proofs from your computational complexity courses. If you look at hardness proofs, usually what people do is they devise what we call gadgets. You construct a gadget, which is some kind of an input that is very difficult for your algorithm to distinguish whether the answer is yes or no, and those gadgets are the evidence for the NP hardness. And one thing that one can notice about those gadgets that people show that people construct in order to prove hardness is they are sensitive to perturbations. So in such gadgets, in such inputs that people construct in order to show hardness, usually if you do a small perturbation of the input, the answer changes. It's an input such that very sensitive to small changes, it will change the answer from yes to no. Okay, so we want to formalize it. So this leads to this question: is the true source of hardness the perturbations sensitivity, or is it just an artifact of the way we know how to prove NP hardness? And the other important question is, are real inputs have this robustness to perturbations, or could it be the case that real inputs are also such that small perturbations will switch them from answer yes to answer no? And okay. So, of course, formally I will always only be able to address the question of, is this the true source of hardness? It's very difficult to formally address the question, do real inputs have this property? So here is my definition of robustness to perturbations. So you assume that you have some input I, and I said that so I have here a robustness parameter rho, and I said that I is rho robust for a problem P. So it is for a specific problem. If for every input I prime, such that the distance between I and I prime is less than rho, the answer on I is the same as the answer on I prime. So of course for this I need to define some notion of a metric between instances. So this is a basic intuition. I say that an input is, so as you assume it, you have a decision problem. For a decision problem, so P of I is a yes or no. That's the answer for the decision problem. So I said that an input I is robust if every close-by input will result in the same answer. It's far from the boundary between yes instances and no instances. Of course, depending on our notion of what is the distance between inputs. And the basic result that I will show is that there are many NP-hard problems in machine learning and computational geometry and clustering, such that if we restrict our attention to robust instances, to perturbation robust instances, we can find a polynomial time algorithm that will solve all the perturbation robust instances. So if we believe that real inputs are perturbation robust, then we have an answer to the question of why is there a gap between worst case complexity and what is happening in practice. One cautious comment is that the complexity of these algorithms will have exponential dependence on the robustness parameter. So the more robust the problem, the faster we could come up with the answer, but the dependence of the robustness, we will show that it's inevitably exponential with the robustness parameter. Okay, so this is kind of giving you the direction in which I want to go. Now I'll be a little bit formal. I'll define what are the kind of learning problems that I'm talking about, and I'll give you a list of problems which are NP-hard, and then we will see how we can handle, for those NP-hard problems, those instances which are robust. Okay? So the basic paradigm that I'm going to talk about, the basic computational problem that I'm going to talk about is empirical risk minimization. So I think probably all of you know what empirical risk minimization is. So we have some class H of subsets of X or of positives, and then we get some labeled training sample S, and we want to find some H in H that minimizes the loss on S, minimizes the error on S. And so this is the empirical risk minimization, and then we'll use it to predict for a new point with this H, and we know that VC theory or whatever tells you that if H is mild enough, then this is a good strategy. This strategy will lead to a solution that generalizes well for randomly generated X's. So, I mean, everybody is familiar with empirical risk minimization, right? Of course, I mean, there are two comments to say, well, why do I care about empirical risk minimization? It's not really the practical way that people do machine learning. So first of all, the same analysis will apply to empirical risk minimization with a regularizer. So adding a regularization will not change the discussion. Of course, the one very common way that people solve it in practice is by using surrogate loss rather than the 0-1 loss. And there's a lot of work on the question of what kind of guarantee can you give for a surrogate loss in terms of the 0-1 or the true loss that you care about. And recently there are results that show that this gap cannot be bridged without running into NP-hards. But that's not the topic of this talk, just to be aware of it. So in practice, people use surrogate loss, convex losses, but those convex losses are not guaranteed to give you results which are close to the true optimum, because those results can have actually sometimes high error, and we run again into the computational complexity issues. Okay, so I'm going to talk here about the ERM problem, and the empirical risk minimization problem translates into a very clear combinatorial optimization. What's the combinatorial optimization? We have this family H of models, and we define the search problem, and the search problem is you get a finite set of 0-1 labeled instances, say for completeness that they are all in Rn. And you want to find an H that minimizes the number of misclassified points in S. So this is now looks very much like a combinatorial optimization, even a computational geometry problem. I give you a set of points in Rn, they're labeled 0 or 1. You have a collection of subsets. You want to find the subsets that captures the most of the ones and the minimum number of zeros. So it's almost translated to a clean combinatorial optimization or computational geometry problem. And for these problems, many natural classes give rise to NP-hard problems. So for each of the following classes, now our problem, our optimization problem, depends on the class H. What are we trying to, where are we searching for the empirical risk minimizer? And for many of those classes, not only that these problems are NP-hard, they're also NP-hard to approximate. So for all of those problems, there exists some approximation factor epsilon null such that it's NP hard to approximate beyond this epsilon null. And here is a list, monomials, monotone monomials, half spaces, balls, axis-aligned rectangles, threshold neural networks. For all of those, empirical risk minimization is NP hard and NP hard to approximate. So these are the problems that we want to see how the assumption that data is robust will help us overcome the NP hardness. Okay, so the next step I have to do is to define what is my notion of between instances distance. Because I want to say that I want to focus on instances such that every neighboring instance has the same answer. So I have to define a notion of neighborhood or distance between instances to my problem. Instances to my problems are such samples, labeled samples. So I define the distance between two instances as the maximum Euclidean distance between the corresponding points. So I assume that I have I look at the best match between the samples here and the sample here. I look at the best match, I look at the same size samples, and I define the distance between them as the maximum distance between xi's.
You assume yi's are the same?
What? And yi's are the same. I assume yi's are the same. So for me, the instances are with the same yi's, and it's the distance between the xi's. And in clustering problems, we will not have this issue of the yi's at all. So it'll just be the best match between the two instances and the maximum distance there. And okay, so just recall our definition is that an instance is robust if for every distance or for every other instance of a small distance they have the same answer. So the interpretation with this notion is that with respect to the distance we just defined, an instance is robust if and only if the output is not sensitive to smaller than rho attribute measurements error. Because you can think of it as how did I get from the instance I to instance I prime? If my measurement has measurement errors, then I'm likely to have additive inaccuracies. So I'm looking at an instance, I think that I'm looking at an instance I, but actually I'm looking at an instance I prime, which is additively close to it. So if I have a patient and I measure all kinds of parameters about my patient, the weight, the temperature, the blood pressure, whatever, I have measurements errors. So if my patient is represented by a vector of those measurements, it's likely that I'm looking at some I prime when I'm actually thinking about I. And I want my conclusion not to depend on these small measurements errors. So this is my way of trying to justify why it's a natural notion. So I want to claim that in some intuitive sense, we would like to look at instances for which these small perturbations will not drastically affect the answer. Okay, so the first type of results, that is the results that I mentioned, I got from Hans Simon in 2000, and for some of the problems, for other problems in 2004, that for each of the above classes, for every value of robustness, there exists a polynomial time algorithm that finds the optimum solution for all row robust numbers. So with this notion of robustness, we really achieve our goal of showing if data satisfies this robustness, there is a polynomial time algorithm. The NP hardness is really limited to the instances which are not robust. The non-robustness is really the source of problems. And one disclaimer is that the complexity of these algorithms is exponential, has exponential dependence on the robustness parameter. So for every fixed parameter, we get polynomial time, but the dependence on rho is bad. And we can show that this is inevitable. Okay, so I'm now getting a little bit even more technical. I want to define, what I want to do is, I want to give you an idea of the proof of this result, and then I want to discuss the cons and pros of such results and some alternative approaches that try to overcome the deficiencies of my result. Yeah.
Are there any results if you choose something other than the max there?
Yeah, that's the kind of things that I'll talk about.
Okay.
So I want to focus on this result. I have to become a little bit more technical. So first of all, what is usually defined as the quality of approximation? So I'll talk about approximation algorithms. In many cases, we don't really need to find the exact optimum. It's enough to get an approximation of the best possible error or the best possible solution. So if we have a notion of the pi, which is the pi of an instance in a solution, is the cost of this solution of this instance, and we are trying to find the instance, the solution that minimizes the cost for this input I. So we said that an algorithm A is an epsilon approximation if for all inputs I, the cost of the solution that A finds for I, the cost on I of the solution that A finds, is within factor of 1 plus epsilon to the optimal cost. Okay, so that's the standard definition in approximation theory. We have an algorithm A, we compare it to the optimum solution. We want to show that this cost is at most the optimum solution times 1 plus epsilon. Then we'll say that this is an epsilon approximation.
I here will be a training set.
I is a training set, right? I is an instance that you, right?
Yeah.
If you translate it to the learning, I is a training set. So you want for every training set to find a solution whose loss is not by much more than the optimal loss which is possible for this training set. Okay, so that's it. And now we want to have a version of this that will be robust to small perturbations. So I define this notion of lambda tau of I. So I have an instance I define lambda tau of I. Lambda tau of I is, so look at what I'm doing here. I'm comparing, I look at the optimum solution for I. But I look at its cost on I, and I look at its cost on I prime. I want to show that, I want to kind of measure, if I change from I to I prime, I perturb I, and I get a new instance I prime. I want that the solution that was optimum for I will still be close to optimum for I prime. So I look at how much the solution deteriorates when I move from I to I prime, and I divide it by the distance between I and I prime. So if two instances are close, I don't want the cost of the solution to change by much. So again, you see this kind of Lipschitzness kind of condition. I wanted that dependence of the quality of the solution on small perturbations will not be dramatic, and I only care about instances which are in the theta neighborhood of I. So there is another parameter here, this theta parameter, which says I have an instance I only look at instances which are in the theta neighborhood of I, and for those instances, I want that a solution that was good for I will not be too bad for I prime. This is kind of my measure of how sensitive is my problem to small changes in the input. Okay? So this parameters models how sensitive is the input I to small perturbations with respect to the given problem. So that's a property of my instance I. Some instances are going to be very sensitive. If in the neighborhood of this instance there is another instance for which what was optimal for I will be very bad for I prime. These will be sensitive instances, and I want to kind of disregard those instances. Any questions?
So just remind me what I actually was. It was the objective of the function?
The objective.
Right.
In the case of machine of the ERM, pi is the empirical loss.
Empirical loss.
So you have a hypothesis, you look at the empirical loss on I, you perturb I a little bit, you want that the same hypothesis will not have a big empirical loss on the perturbed input.
Right, right. But I mean, it could be that opt of I prime could be very different. I mean, it doesn't say anything about opt of I prime.
No, it doesn't say anything about the distance between the two optimal solutions.
Yeah.
just says that if I found a good solution for one of them and I
Use it on the
ju-
other.
just right, just again, the intuition is that as soon as I have measurements errors,
Yeah.
so I got my instance. I thought it was I prime, but it was actually I. Or I thought it was I prime.
Yeah.
So I found the optimal solution for I. I don't want it to be a bad solution for the reading.
It could still be a very bad solution for I prime.
Compared to its
compared to
optimum.
the optimum, but you don't worry about
I don't worry about it. So I'm just saying, you don't. The cost doesn't deteriorate by much by perturbing the input of input. Okay, so that's my notion of I mean, we are going towards a new definition of approximation quality. So that's a new definition of approximation quality. So now I say that an algorithm is a raw approximation if for every input I, the cost that I get, I take an input I apply my algorithm. Now I compare my cost to the optimum, to the cost of the optimum I, but instead of doing here 1 plus epsilon as we did in the standard definition, what we're doing here is I plus this lambda rho of I rho. So rho should be compared to this epsilon. But here it's multiplied by this Lipschitz condition. Which means if the data is very robust, this Lipschitz condition is going to be 0. Yes?
I'm a bit confused about the relation between what you had called P of I and the robustness distribution, and now the opt of I here. So because you said P of I is the solution of the problem for I, right, in the robustness definition.
Okay, so
And
this
that's
is
not the same as this, or is it?
opt of I is the cost of P of I. Yeah.
No, but opt of I
This
is
should
not-
be P of I. This should
Okay,
be
so
P of
that
I.
these are the same. actually.
These are the same. This should be P of I.
So but then in the neighborhood of I, opt of I prime is the same as opt of I anyway, right? So because the definition of the robustness was that
Okay, so the definition of robustness that I had before was that they are the same.
yes.
If they are the same, then this lambda is going to be 0. Because if they are the same, if you look at this definition here, this lambda is the distance between the cost that you will pay for this opt and the cost you
Yes.
pay. They are the same. So lambda is going to be 0.
So you are going to relax the
So what I'm
robustness.
saying is that if you have robustness, then this is going to be 0. So the raw approximation will be just find the fully optimal solution. So for robust instances, this is approximation just saying find the full optimal solution. But for instances which are not robust, I allow you to find an approximate full solution. That's what I'm trying to get here. So if you are very robust, I require that you find the full solution. If you are very brittle, then I allow you, I relax my slack variable and allow you to find an approximation which gets worse and worse as it is less robust. Okay, so this is the comment here. Note that if the instance is raw robust, then the algorithm is required to have a fully optimal solution, because this is going to be 0. Okay, so that I'm just trying to make it a smooth distinction, a smooth translation between the usual requirement to the requirement that I relax for robust data. I want to say for robust data, I relax the requirement, and we can get an optimal solution. Okay, so everybody's either gave up or understands it. Nobody is in the range of wanting to
I
ask
think
some more
you're
questions.
going to slightly relax your definition of row robust, effectively, is what you're saying, right? Because you're not going to require the equality always that you had in the first. I mean, I think that's what was coming. If you go back to your definition of robust,
To which
the original definition of row robust.
the original definition of raw robust was that if you change something, I'm going in the wrong direction. What was it? This definition.
Right. P of I equals P of I prime.
Right.
That may not be always required in your new way you're tackling this.
Right, but this is a sufficient condition.
Oh yeah, sure, but you're going to have a weaker condition you're going to work with.
Right.
Yeah.
Okay, so we were here. So this is my new. So I have this notion of raw approximation rather than epsilon approximation, and the raw approximation tells you should give me the exact solution if I have robust instances, and if they are not robust, I allow you flexibility, and the flexibility can be large if the instance is very not robust. Okay, so the basic properties of the new measure is that I just was saying that for inputs that have high irregularity, the new measure is less demanding than the old measure of approximation, because instead of being just 1 plus epsilon, the way I allow you to be 1 plus lambda, the Lipschitzness times this epsilon. But for trained, robust, regular inputs, this is a very strong demand. I ask you to get the full optimum solution. And of course, hopefully, real-life instances that we care about are going to be robust. So in that respect, we're going to get to good solutions for that. Okay, so the main result that we get is that for all of those problems, so this is just the problems I was talking about, is best separating hyperplane, or best separating hyperplane, best separating homogeneous hyperplane. I mean, all the problems we talked about, in particular k-means. DOB is just finding the ball that captures maximum number of points. I will talk about it in a minute. For every row, there exists an efficient polytime raw approximation algorithm. And or more precisely, the algorithm is polynomial in the input size, polynomial in the Euclidean dimension, but exponential in this parameter rho. So with this relaxed definition, we kind of catch why is it easy to solve robust instances. And this exponential dependence is inevitable unless P equals NP. There is no approximation scheme that will run in time polynomial 1 over rho. So the dependence of the robustness is bad, but it's inevitable. Okay, so I will go now to talking about the proof. And so I will focus on this DOP problem. The DOP problem is a very nice and simple and elegant combinatorial optimization problem. I give you a collection of points. P now, it's a bad choice of, it's not a solution now. P is just an input collection of points in Rn. I give you a collection of points in Rn, and I ask you to find the unit ball that will capture the maximum number of these points. So you have a unit ball in your hand. You want to place it over these points such it will capture the maximum number of points. So this is the densest open ball problem. And we can even assume that all my points are in the unit sphere because this open ball cannot get everything that is lying on the boundary. Okay, so that's, and this problem is known to be NP hard and NP hard to approximate. So I want to solve this problem for robust instances. I want to show it for robust instances and we can have a polynomial solution. Here is a very simple algorithm. So what is a simple algorithm for this problem? You get your input x1 to xm. Look at all d plus 1 tuples from your input. For every such d plus 1 tuple, find the ball that they define, the minimal ball that captures those points, and then count how many points are inside this ball, and go over all balls, count how many, over all balls which are defined by d plus 1 points, and just count which of them capture the maximum number of points. So this is an algorithm that is guaranteed to give you the right answer because every ball in our N, no matter over how many points, is defined by at most d plus 1 of these points. So if I go over all d plus 1 tuples, I consider all candidate balls. Okay? And then you output the ball with maximum intersection with P. So what's wrong with this algorithm? I mean, do you see my algorithm? You get a collection of many, many points. You go over all d tuples. For every d tuple, you find the smallest enclosing ball and count how many points it captured and output the maximum of them. What I'm claiming is that for every ball, you can replace it by one that is catching at most d plus 1 points, because we are around d, and will capture the same number of points. So what is wrong with this algorithm? I gave you here as a nice solution. It's exponential in d, because you have to go over all d tuples of points. Okay. So the problem is that it's exponential in d, so the running time is too much. We don't want to be exponential. So here is a second algorithm that will overcome this exponential dependence on d. And here I'll pick some k which is much less than d. And instead of looking at all d tuples, I look only on all k tuples. Now my running time will be just the input to the power k. So I have overcome the complexity problem. My running time is just this input size to this power k. What is the problem with this algorithm?
Not guaranteed.
Not guaranteed to find the best ball, because I'm only looking at a small subset of the balls. So we don't know that it gives you a good hypothesis. Okay, so the trick is that using robustness, we will show that the second algorithm is guaranteed to find an optimal ball. And so that's the trick. So now, to do it, we need some kind of a theorem, which I guess is folklore. Many people know it in different names. And also, this is a nice geometric theorem. It says the following. Assuming you have a subset of the d-dimensional ball, then every y in the convex hull of S, there exist k points such that the distance between y and the average of these k points is at most 1 over square root of k. So maybe I'll just draw a picture. So you get a collection of many points. This is S. So now I look at the convex hull of this set. And I pick some target point y that I want to approximate here. And the claim is, I have to put it in the convex hull. The claim is that for every k and for every y that I pick, I can find k points here such that when I take the average of these points, it will be very close to y. How close to y depends on how many points I picked. So what we see here is that if I picked k points, I can guarantee to approximate y to within 1 over square root of k. So the more points I pick, the better I can approximate any point in the convex hull. Why is it relevant to my problem of minimum enclosing ball? Because I know that the optimal solution, the center of the ball that covers the maximum number of points, is inside this convex hull. So by using just k tuples, I can approximate it up to this distance. But if the solution is robust to small perturbations on the inputs, then the fact that I thought that this was the center or this was the center will not change the number of points that I captured. It's just that I took all my points and shifted them by a factor of 1 over square root of k, and the solution is still the same solution. So by doing this approximation, I did not miss any quality of the solution. So that's the basic idea here. So for all of these problems, we get an algorithm that runs in times and the input size to the row to the power minus 2. The row to the minus 2 is just because the k that I need is the relationship between the k that I need and the approximation. If you are 1 over the square root of k robust, then I need k points. So if you are rho robust, I need rho square points. If I need rho square points, my running time will be n to the power 1 over rho square. 1 over rho square points. Okay, so we get this optimal solution for all robust instances. Yes?
Your algorithm seems a bit overkill, because here you could just use the average. You don't have to find the best ball to contain it. I mean, because I thought in your algorithm 1, you were looking for the smallest ball that contains the points.
Right, but you could also go take...
You just take the average.
The average,
yeah.
Right. But just the complexity comes from how many tuples do I have to consider. So I'm only taking the average, but I'm going over all k tuples, and for every k tuple I take the average.
Yeah.
And the result, the geometric result, just tells me that if the data is robust to small perturbations, then among the fewer balls that I will consider, there is one which is optimal. Okay, so in comparison, the worst case complexity of the smallest and closest ball is NP hard for some fixed approximation value. Okay, so here I already gave you the proof idea, so I don't have to repeat it. Let me just compare it. So what I'm going to do next is just compare it to other solutions to the same type of problems. Now, and one more comment before I continue is that if I have a solution to the densest ball problem, I also have a solution to finding the best half space that separates plus and negative points, because I can always take all my points and project them on the ball, and take all the negative points and project them to the other side, and then you can see that the best hyperplane that separates the minuses and the pluses is the hyperplane that captures the maximum number of points after I projected all the minuses to their antipodal points. And by finding the best hyperplane, it's very similar to finding the center. If I knew what the center of the best ball that captures all of those points, then the best hyperplane is just the hyperplane that points in this direction. So from the densest open ball problem, I can get to half spaces, I can get to neural network solutions, and I can get to k-means. For k-means, I just have to repeat it, look at all k times so many points, and approximate each of the possible centers. So I'm not doing it formally, but I think it's believable that the same technique now applies to all of this family of problems. Okay? So the next I want to show, to compare it to other proposed solutions. So one natural candidate, first candidate to compare to, which is an older solution, is the smooth analysis by Spielman and Telk. So what is the smooth analysis? So they focus on a specific algorithm. And the smooth complexity of an algorithm is that you take every instance of the algorithm, and for every instance of the algorithm, you take a ball around this instance and look at the average complexity of this algorithm if the inputs are randomly chosen from this ball. And instead of looking at the complexity of the runtime of the algorithm on the instance, you look at the average runtime over all instances that sit in this ball. And they can show that this is another way of saying hard points are isolated. Because the smooth complexity of a problem, of an algorithm, is the worst case over all points, but instead of looking at the runtime at the point, I look at the average runtime at the ball of instances around this point. So it has some kind of a similar flavor, but it's different in at least two respects. First, this is an analysis of a specific algorithm, and my notion is a notion of complexity of the problem. And the second difference is that the smooth analysis, takes the average of a random perturbation of the input, but the worst case over all points. And we are doing something different. We are just restricting our attention to those instances which are nice. So it's not, they are saying every instance has nice instances in its neighborhood. We are saying you don't care about not nice instances, just focus on the nice instances. So it's a different approach to a similar problem. Okay, so now I want to talk about other proposed solutions. And before I do that, let us try to think kind of in a high-level way, what properties do we want from a notion of easiness of input? I want to have a notion of easy input, and to show that on easy input, my problems are not so hard. So what properties do I want? So what is the desiderata for notion of well-behaved inputs? So the first thing that I want is that it is reasonable to assume that most, or at least significant proportion, of the inputs that one may care about in practice are well-behaved. And this is a kind of a vague requirement, but it's an important requirement. If you have a notion that tries to explain why things work well in practice, it has to somehow capture which instances you think you'll get in practice. And it couldn't be all instances because we know that those problems are NP hard once you consider all possible instances. Okay? The next is, of course, an obvious requirement. There should be an efficient algorithm that is guaranteed to find a good solution for all well-behaved inputs in a efficient time. So these are the two requirements we've talked about so far. But actually, if you think about it more, there are more desirable requirements. So other desirable requirements, for example, is that there exists an efficient algorithm that, given in an input, it can figure out whether the input is well behaved or not. I mean, that could be a very nice property. If I have an algorithm that only is guaranteed to work on nice inputs. So now you get some input. Maybe you are unlucky and this input is not nice. So it would be very good if you could just somehow look at the input and tell me, okay, don't run your algorithm. It's bound to die, right? And if your problem is a decision problem, you can, I mean, if it's SAT problem, you can say, okay, run the algorithm, run it for so much time, see if it gave you a good solution. If not, I mean, you can test it. You got, and whether the solution is good or not. But problems like clustering, there is no way you can test like if the clustering that you got was a good clustering or not. So you can't have a self-testing algorithm. So it would be very nice if you could test whether the input is such that I have a guarantee of success for this input or not. And we don't. It's very difficult to get this kind of property. Another important property, or somewhat important, is that it would be very nice if we could show that explain why commonly used algorithms are used in practice succeed. Not just come up with a new artificial algorithm, like the artificial algorithm that I showed you for the densest open ball, but show you why real algorithms that people actually use, why they work. And so now, so we have a list of desirable properties. I can ask, how does my solution fare with respect to those desirable properties? So I do believe that my additive perturbation robustness meets the realistic input requirement. I tried to explain it to you before. I kind of sufficiently convinced that it's a good notion from that respect. In terms of does it satisfy the second requirement, does it give you efficient runtime, it is polynomial, but it's not practically efficient. Because we have this exponential dependence on the robustness parameter, when we try to run it in practice, it's too much. So it's polynomial time, but a bad polynomial time. So this satisfies only halfway. In terms of testing, there is no way we can test our inputs. And in terms of having a good practical algorithm, we don't have this requirement. So we could answer 1.5 of the 4 requirements. It's not ideal, we are far from a solution. So let me now mention some other solutions that other teams have proposed recently. So the first one was really the paper that called attention to this direction of research. That was the paper of Bilu and Linian from 2010. And they did something very similar, but instead of talking about additive robustness, they talk about multiplicative robustness. So what's multiplicative robustness? You want that for every 2 points, the distance between those 2 points in I prime is at most an alpha factor of the distance between those 2 points in I. So you are allowed to change distances proportionally rather than additively. So if you have a small distance, you're not allowed to change it by much. But if you have a large distance, you can change it by a lot. There is a question how natural that is and what are the results that you get. Another condition, an interesting condition, is epsilon separateness, was proposed by Ostrovsky and a group of other people. And what they actually looked only at one problem. They look at clustering problem and k-means clustering. And they say, when do I say that my input is really a clusterable instance with respect to k-means? And they say it's a clusterable instance with respect to k-means if the cost of k-means clustering it is much better than the cost of k minus 1 means clustering. So assume that I have data like this. And I want to tell you this is 4 clusterable, but it's not 3 clusterable. Why is it not 3 clusterable? Because the best clustering to 3 clusters will have to take 2 of those and put them together. Maybe this is the optimal 3 clustering. And this has a high cost because those 2 balls are together. In comparison, if I have 4 centers, suddenly the cost reduces by much because I never have to go across this distance. And it's even more acute if my clusters look like this. So now, a 3 solution will have this cost. A 4 solution will only have a cost which is relative to the radius of those blue balls. So they say data is epsilon separated or epsilon clusterable if the k-mean solution is epsilon square better than the k minus 1 optimal solution. And then there is the notion of uniqueness of optimum that was proposed by Balkan and Blum, and it says that an instance is C epsilon approximate solution if whenever you get a cost which is C close to the optimum, this solution as a clustering is close to your optimal solution. So again, a picture here. So assume that I want to cluster this into 2 clusters. So this is an optimal solution. This solution has cost which is very close to the optimal solution, but it is very far as a clustering. So this doesn't have a unique solution. Unique solution are those instances for which if you take any solution that has cost close to the optimum, it looks very similar to the optimum. So that notion was also proposed in this project. And the last one I want to talk about, and this is the key one, is the notion of alpha center stability. So what is alpha center stability? It says that, again, it talks about clustering, it talks about k-means or center-based clustering. And we say that an instance is alpha center stable if you look at the optimal solution and you look at the centers of the optimal solution, every point is closer to its own center more than alpha times its distance to any other center. So if I take a point x and I look at its distance to its own center, and I multiply it by alpha, it is still less than its distance to any other center. It means every point is much closer to its own center than to any other center. It's a very strong notion of clusterability. Right? I cannot allow you something like this, because this point, its distance to the center here, is not much more than its distance to its own center. The alpha center robustness will say every point is at least 7 times more close to its own center than to any other center. So why do I mention it? I mean, for all of those notions, we get, so how do these notions fare with respect to the list of desirable properties? All of those notions imply the existence of an efficient clustering algorithm. In terms of having a verification, none of them allows you to verify whether an input is good or bad. If you notice, all of them, in the definition of what is a good instance, we're talking about the optimal solution. A good instance is defined with respect to the optimal solution, and we never know what the optimal solution is. So nothing here is verifiable. In terms of the epsilon separateness is special in the sense that it shows you that a given algorithm will run optimally. So this idea that the 4 clusters cost much less than 3 clusters, it allows to show efficiency of the usual Lloyd-type k-means algorithm. You don't have to come up with a new algorithm. Under this condition, the most common k-means algorithm is guaranteed to work well, with some small modifications. So that's a nice property of the epsilon separateness. However, all of those, except mine, seem to fail the requirement for being realistic. Now, failing this requirement to be realistic, I can state it in a more formal way. And for that, I have to recall there's a provable reason for concern. What's the provable reason to concern? All of the proofs of efficiency of all of those algorithms, the first step is to show that if you have my condition, then you have alpha center stability from some alpha. So all of them, if you look at the proofs, the first step in the proof is showing if you satisfy my condition, then every point is closer to its own distance, to its own center than to any other center. Of course, the question is, by how much? What should be this alpha? So in the bilinear, this alpha was terrible. This alpha was square root of n, dependent on the input. Then they improved this alpha to 30. Then Balkan and her students improved this alpha to 3. So that looked very promising. Every point, I mean, we're making progress. Every point should be 3 times closer to its own center than to any other center. It's still not practical, but it's making progress. I mean, in real data will not have this factor of 3 closer to your own center than to any other center. But we went from factor of square root of n up to 3. Maybe we can push it further. But then came a result this year of Ben-David and Raising. I say Ben-David and not BD because it's not me, it's my son. And they showed that for every alpha greater than 2, solving the alpha center stable is NP hard. So those results, when you keep improving your alpha, will never give you something for alpha less than 2. So all of those approaches will never be able to handle instances in which the distance of a point from its own center is no less than half the distance to any other center. So there is a limit to how far they can go.
Shouldn't there be alpha smaller than 2?
What is it?
Yes.
I think so.
For any alpha smaller than 2, right. Can think. Yeah. For any alpha smaller. It's NP hard, right. For any alpha less or equal than 2, it's NP hard, right. Yeah. So there was a hope that this kind of approach will get better and better and better, but it's not. So the conclusions are that the new measures kind of detect hard instances, but it's not clear that they are realistic inputs. A big question is, can we do something similar for SAT? And I have no clue how to do it, or for traveling salesman problem, or for any other famous NP hard problem that people apply in practice. And will the new analysis, type of analysis, lead to new interesting algorithms? So far, the algorithms that came out of the analysis are not interesting from a practical point of view. Okay, thank you very much.
Questions?
Yeah.
Okay, now, didn't you just say the only reason you have to believe that inputs that fulfill your condition are realistic is that you believe that they are, because you can't check it, right? So actually, the claim that the inputs that you define are realistic or natural, that's just, I mean, nothing backs that up, or doesn't it?
Yeah, I cannot test it because I cannot find the optimal solution. But I can have some kind of heuristic argument why I believe that real instances should be like that. I mean, I believe that realistically, I mean, it's like the phrase that was coined by Danieli and Linear in a different paper is that we believe that clustering is hard only when it doesn't matter. So they try to argue that when you have instances which are not robust, you don't really care to cluster them because there is no real cluster structure.
But you do clustering often in situations where there is not, and there are very good reasons for doing that.
Right, right. So I think, I mean, the variability is a very painful deficiency of the solution that we have so far. I mean, I think this direction is more about telling you, here is an exciting research direction that is really making its first steps. I mean, we don't have any definite, complete answers. There's lots of directions in which one could hope to improve. Or show that it's really the case that, I mean, I don't know, for SAT, you see it working all the time. I really believe that there should be an explanation why it works. And similar for other problems in machine learning. I mean, you can say, you can rephrase the problem and ask, why are the solutions that we find by a kind of a surrogate loss, for which I can calculate it, why are they good solutions? And the claim that the surrogate loss is an upper bound to the true loss is not completely answering the question. Yes?
When you had your distance for robustness and you had the maximum over the Euclidean norm of the distances, if you soften or refine the maximum to like a 2 norm or a 1 norm over the sequence, how do results change?
Right, so the results get weaker, but you can still push it through. You can still get the result, but it gets a weaker result. The approximation quality becomes weaker. But to me, the point is that all that is behind my proof is a very simple geometric trick. And I don't think that this should be enough to explain why sophisticated algorithms succeed in practice. So I don't believe in it enough to keep pushing it to its limits. I think there should be other directions of explaining why things work. Yes?
I'm not sure I know fully how to express this, but it seems to me to relate in some sense to the boundaries in input space between solutions.
Right.
And we're really, to avoid pathological, to satisfy your
requirement
your
that
requirements, you need for
without
those
pathological inputs, right?
Without pathological inputs, you need for those boundaries not to be dense.
Right, it's very similar to my probabilistic Lipschitz conditions I was talking about statistically. They have a very similar flavor. I mean, they come from the same mind, but they cannot show a more exact matching.
Okay, but I've understood the issue. Okay. Any other questions?
Okay.